My name is David Sliney, and I'm going to introduce this section for the Certified Management Consultant on UVC. And this is an introduction to germicidal ultraviolet radiation. We have a few goals for this section. I want to just initially provide an overview and an objective for the whole course, and provide a background and concepts of GUV. I think it's worthwhile to know something about the history and value of GUV, and it's important also to know the jargon or the special terminology that we use when we utilize germicidal UV. I also think it's important for all of us to be aware of the basic quantities and units that we measure when installing and assessing a germicidal installation. And probably one of the most important objectives of this course is to allow you to fully understand the importance of safe installation and use. Now, this objective for this section is we want you to be able to describe to users the history and value of germicidal UV. We want you to know the physical terms, the quantities and units used when describing a dose from germicidal UV. It's important, we think, for you to be able to distinguish between ultraviolet spectral bands, UVA, UVB, and UVC, as we'll chat about in a minute. And we think it's important for you to understand the relationship between UV dose and dose rate, that is, the total exposure and the exposure rate, and time of exposure is very important. So let's get started and give you some background. First of all, I want to impress upon you that germicidal UV is hardly new. It's been used as UVGI and many different terms, but it's most typically today known as GUV or UVC. UVC refers to the short wavelength in the ultraviolet spectrum. GUV has been applied for well over a century, and I can tell you, as a young boy back in the 1950s, that I can remember seeing germicidal lamps in public toilets and medical facilities in many places, and they went out of style back in the 60s and 70s because we made major medical breakthroughs with the development of the polio vaccine, vaccines for measles, mumps, and so on, and typical childhood infectious diseases. So there was less enthusiasm for controlling it if we didn't have a vaccine. Well, there's been a renewed interest in GUV in the last few years because of the COVID-19 pandemic, which is the result of the SARS-CoV-2 vaccine or virus. And it took a little while, but I think all the experts eventually agreed that this is an airborne infection. So germicidal UV is particularly effective for airborne infections where transmission occurs through the air and people's exhalation. It's not surprising then there's an increased interest in disinfection. But I want to impress upon you why it's so important to have GUV certification, because this technology is very effective, but it has to be used safely, or people can get injured. And this can be a death knell for a particular installation when somebody thinks they've been injured and they protest. So you've been chosen quite possibly because you already have some experience in NALCO for installation of lamp equipment and lighting equipment, and an expertise in lighting installation, maintenance, and service provides an ideal background for applying GUV, both for installation and for maintenance, because improper installation and service of GUV luminaires can cause injuries. Acute injuries, they're not really severe, but they can be very unpleasant. So expert installation is critical, and this is your role. Now, I told you I'd say a few things about germicidal UV history and point out that it's been used quite effectively since the 1930s. In Duke University in North Carolina, they investigated the reduction of hospital-acquired infection from using upper and general room ultraviolet C during surgeries, as we see in this old photograph on the left. This reduced hospital-acquired infection. And we think that it's time to rethink that and perhaps restore some of that thinking in modern surgical suites. In any case, as I pointed out, GUV was widely accepted and widely applied in the 1950s before the vaccines for measles, mumps, and polio and so forth were not available. Now, the use diminished because of the development not only of vaccine, but of antibiotics and germicidal disinfectants, chemical agents that would be helpful. However, germicidal UV remained in one area where they didn't have a vaccine, and that's to control tuberculosis or TB. And so you still find them in TB wards. So there's been a revitalized interest with multi-drug resistant TB strains and COVID-19 and microbes that are aerosolized. So the development of the drug-resistant TB strains and COVID-19 really excited renewed interest for germicidal UV. I might mention that back in the 1950s, germicidal UV was widely used in a lot of biological laboratories. It still is to some extent, but not as extensively as it was back in the 1950s, because it could inactivate biological aerosols and greatly reduce the chance of infection in animal facilities and various biological research. So we see some stick figures on the left there, which actually came from an old General Electric company brochure, sales brochure on different types of use. And you might notice that the lamps being used are radiating in different directions depending upon the application. Now, I think it's really interesting to realize how airborne transmission really takes place. Normally, if we're just standing in a room and breathing without talking, our breathing zone will be fairly limited, less than a foot. But if we're talking, that starts to extend out to a couple of feet. And this was actually the basis for the CDC guidelines during the COVID epidemic for safe distancing, social distancing, stay 6 feet apart. If you're 6 feet apart, even if you're singing, chances are your breathing zone won't extend to the next person. So today, the big value would be in inactivating viruses and other microbes where we don't have a vaccine. And unfortunately, we are short of people who understand how to properly apply the technology. It's not widely understood how effective it is. Now, the past use of germicidal UV was largely in the area of upper room germicidal UV lamps, low pressure mercury lamps, which have been in use for decades. And not only the development of vaccines, but also misunderstandings about safety led to unwarranted concerns. And you only needed one accidental overexposure where someone had a very unpleasant, painful eye surface injury that immediately cleared within a day or two, but it was not pleasant. And once you have somebody who's been accidentally exposed, they can be quite insistent on not just fixing the LED or the germicidal installation, but actually having it removed entirely. So we're convinced that industry needs to do a better job in explaining the safety and proper use of germicidal UV, and it desperately needs competent people to apply this technology. Oops. So I clipped this out of a CDC educational brochure on how upper room germicidal works. Basically, you have to have a reasonably high ceiling, well above the position of staining individuals, and you disinfect that upper room air. And there's normal air mixing in any room, even with poor ventilation, such that the infected air will eventually drift up there and be disinfected by the germicidal fixtures that are over on the left-hand wall there in this example. Now, before we get too much further, I want to try to point out the standard metric units that we apply when we're talking about exposures, exposure doses, and dose rates, and so forth of UV. There's the international consensus units, the Système International, or SI, System of Physical Quantities and Units. And the fascinating thing to me is that almost all of the physical measures that we use can be expressed with only 3 fundamental units. These are the meter, the kilogram, and the second, or length, mass, and time. Now, in lighting and germicidal UV, we're going to talk about wavelength. And in the ultraviolet and the visible spectrum, we normally measure that in a unit of nanometer, which is a billionth of a meter. Remember, a meter is about 39 inches. Now, obviously, we have a lot of other units than distance and time and mass. But this tabulation shows you how some important quantities that we'll be using energy and power are actually related back to those fundamental units, the three fundamental units. I want to point out that energy measured in joules is watts of power delivered multiplied by the seconds of delivery. So 1 joule is equal to 1 watt delivered in 1 second. There's only one quantity and unit in the SI system that's not based upon these three fundamental quantities. That's the lumen, defined by the spectral response of the human vision, V lambda. Well, not that you need to remember these definitions, but I wanted to introduce that we need to talk about wavelength. We need to talk about energy and energy per unit area delivered, and watts and watts per unit area delivered. And we'll get to that. I also want to remind you that in the SI system, we make use of a lot of multiplier terms like kilo and milli and micro and nano. And in this table, we see the standard symbol for kilo and milli and micro. There's a typo there, and that second M should be mu, or a Greek M. But this is the fractional value of these things. We don't have a room for enough zeros in front of one for nano, which is 10 to the minus ninth, or a decimal point with 9 decimal places to the right before you get to a unit. So I also want to mention that GUV is almost frequently in the past referred to as germicidal radiation. We tend not to use the term radiation too often when we're talking about UV, because the average public sees the term radiation as ionizing radiation, which is, we all recognize, potentially hazardous. And we don't want to over-demonstrate or over-emphasize the potential safety issues with improper use of germicidal UV. So we just use the term germicidal UV. Some people refer to as germicidal UV light, but technically some people take issue with that. So anyway, the whole spectrum of different radiations are listed here, everything from radio waves to infrared, visible, ultraviolet, X-rays, and gamma rays. All of these collectively are known as electromagnetic radiation. You may hear that term from time to time. And the whole spectrum across this many different range of wavelengths is referred to as the electromagnetic spectrum. And we see also here in this figure the definition of wavelength, which is a distance from crest to crest in a wave. And the term electromagnetic radiation comes about because radiant energy is characterized by both an oscillating electric field and an oscillating magnetic field. The magnetic field oscillates in one plane, the electric field in another, as illustrated in the slide. So across the electromagnetic spectrum, if we start from the right-hand side here and go towards the left, which is increasing the wavelength and shortening, increasing the frequency and shortening the wavelength, we see that we go from the radio waves to microwaves to infrared, the visible, then the near ultraviolet, and the far ultraviolet, and middle ultraviolet. And if we go to shorter wavelengths than ultraviolet, we get into the X-ray region and gamma ray region. And these radiations are what we generally think of when we're talking about radiation hazards. That's also termed ionizing radiation. The optical spectrum gives the ultraviolet, the visible, and the infrared. And I want to emphasize here how narrow a bandwidth that we have for seeing, because it goes from about 400 to almost 800 nanometers, which is a factor of 2 in wavelength. But if we look at the whole infrared spectrum, that's 1,000-fold change, not just a factor of 2, 1,000-fold, from less than 1 micrometer all the way up to 1 millimeter. So that's very important to keep in mind, that we have to be careful not to assume that if we see something in the visible as being white or highly reflective, it may not be highly reflective in the ultraviolet or in the infrared where we don't have good vision. In fact, it could be just the opposite. We could have an enhanced reflection in the ultraviolet or infrared. So keep that in mind when you're looking at a installation and looking at walls and trying to speculate on what's going to be very reflective, because sometimes a black metallic paint is much more reflective than a white powdery paint. So the takeaway is, don't assume that the reflection and optical characteristics of a surface are the same as what you see in the visible, because you're limited to a very narrow range of wavelengths and frequencies. Now, some of you might have asked, you've heard about photons of light, and there are some phenomena in optics that are better described if we think in terms of little packets of energy rather than as wavelengths. And so as we get into the UV, and particularly in the ionizing radiation, the photon energy makes a lot of difference, because some shorter wavelength UV photons are very effective at killing viruses and other molecules, and not so effective, say, in the visible or the nearest ultraviolet band, or the UVA. So here we see the UV spectrum, and we see that there's UVA, UVB, and UVC, and then the vacuum ultraviolet. And eventually, if you go below the ultraviolet band, we get into X-rays. And if you go too far into the visible, you can actually get to some infrared. So, summary points. UV radiation falls between the visible band and the X-ray band in the electromagnetic spectrum. The second key point is that UVC is that spectral region which is the shortest of the UV wavelengths, from about 100 nanometers up to 280 nanometers. That's pretty well agreed by the CIA and the IES and other organizations interested in lighting and light technology. The only really effective germicidal region of the spectrum is UVC, probably because the photons are already pretty well controlled. And the key takeaway here is that the UVC is roughly from about 280 nanometers at the edge of the vacuum UV to 280 nanometers at the edge of the UVB. UVB is important because this is what causes skin cancer from excessive repeated exposure to ultraviolet and sunlight, even though it's a tiny trace amount of the whole solar spectrum. So I might also mention to some of you who are not into the science side is that this little figure here is a Greek L, lambda, and that is what we use to symbolize wavelength. Now, there's another point of interest before we leave this subject of the germicidal UV bands, and that is the photobiological spectral band designations that were introduced many years ago by the CIE Committee on Photobiology. Remember, CIE is International Commission on Illumination. CIE stands for the French words that make up International Commission on Illumination. And they have a committee on photobiology, which came up with this thing, which today is considered really quite useful. We break the ultraviolet into 3 spectral bands and the infrared into 3 spectral bands, in addition to, of course, the visible. I might mention that the visible light overlaps into the UV and the infrared. And the reason is that there's no sharply defined edge of the visible spectrum and suddenly you're in the UV or suddenly in the infrared. Instead, there's an overlap. And so it depends upon how bright the source is as to whether you see it, rather than whether it's in the near UV or in the visible. The spectral band known as UVC is what we generally also refer to as the germicidal band. Now, there's some bands in the infrared, but since we're not talking about that today, I won't go into any further discussion on that. I mentioned that the UV band is right on the edge of the ionizing spectrum, and it's quite a careful approach needed when we're talking to the public about radiation, because as soon as you say germicidal radiation or something like that, they're thinking of X-rays and gamma rays, and they've been subjected to a lot of public health campaigns to make people concerned about radiation. But when that's the thrust of the discussion, they're talking about ionizing radiation, where there really is a public health concern. Now, the optical spectrum, as well as the radio frequency spectrum, are together referred to as non-ionizing radiation. You have to get up shorter than, say, 230 nanometers. So let's summarize then. UVC is the most energetic ultraviolet spectral region because the photon energy goes up as you get to shorter and shorter wavelengths. And that's why shorter wavelengths are more effective in causing not only biological harm, but also inactivation or countering some of the useful effects of germicidal UV. It's also a nice takeaway to recognize that the UVB in sunlight is very intense and helps disinfect the outdoor air, particularly in the spring and summer when there's a much higher environmental UV index in the winter than in the summer. There have been claims of using visible light, deep violet light, or UVA for germicidal applications, and they can show in the laboratory that it can have a germicidal effect. But unfortunately, the efficacy, the effectiveness of those wavelengths is so poorly known. We don't know whether you're going to come back. Okay. Now, I want to add a few basic UVC questions, because you may well be asked these questions by your customers. Questions like, how does UVC disinfect? How effective is it really? And are some UV rays more effective than others? So let's just review quickly what's happening when UV is damaging and inactivating viruses and molds and bacteria. Well, the target molecule for UV damage is normally what we refer to as deoxyribonucleic acid, or simply DNA, which play a critical role in the cell nuclei of any cells. Now, I hasten to add that viruses are not technically cells, and they're just biological agents. But we won't go into further detail on that. However, the influenza virus, the RSV, SARS-CoV-2 are RNA viruses, and they don't even have cells, and they don't have DNA in a pure form. It might be in an off-axis angle, and we miss them to see their contribution. Another point that is useful to keep in mind is that not all wavelengths are the same. Some wavelengths are much more effective, or they might be more hazardous too. And photobiologists use the term action spectrum to describe the relative efficacy of radiant energy at different wavelengths in the ultraviolet. And we see an example of what used to be called the standardized germicidal action spectrum. Today, that term is discarded because we recognize that every virus and mold or visible light that we encounter from day to day may or may not have much of the key wavelengths that are shown in this action spectrum slide. Other bacteria and different organisms have slightly differing action spectrum, but as general, the wavelengths around 270 nanometers are probably the most effective. There has been a growing interest in germicidal UVs ever since COVID-19 was recognized as being an airborne virus. And so it's becoming an increasing area of scientific study. The action spectra for inactivation of different hazardous molecules or cells, such as bacteria, or molds, or viruses. There have been UV sources placed on the market, which I mentioned previously, have shown some efficacy, but the efficacy is so small relative to germicidal UV that we don't normally even consider that for applications. Now, I have a couple of figures here to try to explain the concepts of dose and dose rate in photobiology. First of all, we have to recognize that the total power coming out of the lamp is important. But for any given surface that is going to be disinfected, including your skin, we need to know the watts per square centimeter or per square meter. And this figure on the right gives you an example of what we're trying to describe as the irradiance, or watts per square centimeter. And it's also useful to remember that there are units of milliwatts per square centimeter and microwatts per square centimeter that may be more common. As I said, the irradiance is often referred to as a dose rate, and the total accumulated radiant exposure, and H in terms of questionable UV is right there. Okay, so the safety guidelines for germicidal UV are promulgated by the American Conference of Governmental Industrial Hygienists. That's a mouthful, or just ACGIH, and we see their little threshold limit value book. They have limits for benzene and for oxides of nitrogen and carbon monoxide and ozone and so forth. But they also have threshold limit values or maximal exposure limits for other airborne contaminants, such as those gases and fumes that I mentioned, but also physical agents such as noise and heat stress and optical radiation. The key things to realize are that the limit is normally expressed as a dose, as an exposure dose or a radiant exposure of 3 millijoules per square centimeter, maximized to 270 nanometers, and it would be higher at other wavelengths. This dose is equivalent to delivering a low dose rate of 0.1 microwatt per square centimeter for 8 hours. You'll come up to about 3 millijoules per square centimeter. Now, I mentioned that there can be some very unpleasant accidental injuries of the eyes and skin, mostly to the eyes from overexposure to germicidal UV. The other thing that makes it difficult for people to appreciate is that it doesn't appear immediately, the injury to the cornea surface of the eye. It takes several hours. And this is just the characteristic of photobiological injury. The individual UV photons interact with key biological molecules like DNA or certain proteins or enzymes, and activates those. So it's the number of photons in that volume absorbed, and pre-absorption can protect you. For example, the outermost surface layer of the skin protects you against more deeper penetration of UV rays that might injure the germinating layer of the skin, known as the basal layer of the epidermis. Now, there's a delayed effect also, not only of ticklishness or dry eye or even pain. It normally will take several hours for the exposure to become clear to you that, oops, you did walk in front of the germicidal UV source. So what happens? Well, you can get a little reddening of the skin, which we mostly call sunburn. The technical term is erythema. And it might feel sort of itchy and dry. The other type of adverse but temporary injury is that of the cornea, the outermost surface of the eye. And you see in this photograph in the upper left, an individual has bloodshot, what appears to be bloodshot eyes. The good news is that these are almost always disappearing after 10 days or certainly a couple of weeks. So I want to finish by wrapping up with a few summary concepts. Number one, germicidal UV has been around for over a century. Germicidal UV has been shown to be effective and can be safe, provided the designers and installers understand the basic rules of safety and what wavelengths are most effective. That said, we should conclude that your personal role will be important. If you can reduce the chance of somebody getting overexposed and having a somewhat painful experience that evening, you would definitely be worried about individuals not following all the safety rules in your facility. And you need to realize that you may be the first line in the whole technology of germicidal UV to actually be talking to the general public. And so it's very important in our view that you have this more in-depth understanding of the safety issues associated with germicidal UV and how to explain to the general public that if somebody gets injured, it's because of misuse or misapplication of the technology, faulty installation. And that's your role too, because we want you to make informed recommendations for any given installation to make sure that it's safe. Thank you.